Homogeneous second-order linear differential equations. So we were doing this, we got AY prime prime plus BY prime plus CY equals 0. We propose a solution of the form some constant e to the lambda t. We sub that in with its derivative and its second derivative. We sub that into the left-hand side, set it equal to 0. Trying to figure out what lambda is equal to, what the eigenvalue is equal to. We get our auxiliary equation. Solve the auxiliary equation for the two eigenvalues, and we get our homogeneous solution of some constant e to the lambda 1t plus some constant e to the lambda 2t. How do we figure out the constants? Initial conditions. Let's do another example. So here I've got y prime prime minus 4y prime plus 4y equals 0. We'll throw down our auxiliary equation. Our auxiliary equation, lambda squared, matches the y prime prime. The 1 lambda matches the 1 prime. And the no lambdas matches the no prime. We can solve that, and we solve that for lambda. That'll factor into lambda equals 2 and 2. This factors into lambda minus 2 times lambda minus 2. So I get, in this case, real and repeated roots. If I follow through the same procedure then, the same procedure as we were doing when we got real and different roots. Oh, they're both positive, so already if we are following through the same procedure as the last video, we would say the limit as t approaches infinity of the homogeneous solution, or what the homogeneous solution eventually becomes, is infinity. But let's go ahead here. We'll make a linear combination of our two solutions. And, okay, I already start to see problems. Our two solutions are the same. We make a linear combination of them. We end up, we could write this as factoring out the e to the 2t. We could write this as c1 plus c2 e to the 2t. Now it looks like I have two constants, but I really don't, because these two constants kind of collapse down into one constant. If I'm trying to have y naught is equal to 2, that means c1 plus c2 has to equal 2. If I'm trying to have y prime naught equals 0, that means that c1 plus c2 has to equal 0. So I get that the two constants have to add to give me 2 and add to give me 0. I do have two constants in there, it looks like, but I really don't. They collapse down into one constant. So this is a problem, I guess we can say. So how do I fix that? Well, the eigenvalues are 2 and 2. I tried to do the same thing that we were doing before, where I take a linear combination, some constant times e to the 2t plus some constant times e to the 2t, and that didn't work. So I guess they both can't be constants. Well, how about I change one to a function then, a function of time? It's a zeroth. I'm going to change the c2. The c2 right now is a 0th order polynomial in terms of time. What's the next most complicated level up? Let's make it a line. So this is in the place, this c2t is in the place of where c2 used to be. So we went up at one level of complexity. It was a 0th order polynomial, a constant. It is now a 1st order polynomial, a line. So I can still factor that e to the 2t out, but I'm going to get this, c1 plus c2. So now, does that solve my first problem? The problem I had was I couldn't meet these two conditions going through the point 0,2 at a slope of 0. I couldn't meet that the way the constants were set up. Can I now? Well, when I make t equal to 0, y is equal to 2, that gives me, that tells me that c1 has to be 2. Check that out. That's invoking this first condition on this equation. For the second condition, I'm going to need y prime. I'm going to need to differentiate this. I need to match these two initial conditions with my new version of the homogeneous solution. See if I can dial in the C1 and C2 to match. I've got the derivative here of the homogeneous solution as well. Let's sub in, let's do the first condition. When t is equal to 0, y is equal to 2. That means that 2 is equal to, I'm making t equal to 0 here, that's going to be 2 is equal to C1. In this, the second condition is the derivative is equal to 0 when I make t equal to 0 in the derivative. When I do that, I get, okay, I'm making t equal to 0. So this piece is 0. These two e's are 1. And I already know that C1 is equal to 2. So that tells me that C2 must be equal to minus 4. So my solution then, my solution to this differential equation is 2e to the 2 minus 4 t e to the 2t. So 2e to the 2t minus 4t e to the 2t. All right. Well, I'm calling it my solution. I do know that this satisfies the two initial conditions. I'm good with that. And I know that this part of the differential, of the solution, satisfies the differential equation. How do I know that this? I need to show that t e to the 2t is also a solution to this differential equation. I need to show that if I throw a t in front of an e to the lambda t, that it's also a solution. That's not part of that. That doesn't count. That isn't like what we did last time in the last video, in the previous video where we took a linear combination. This is not a linear combination anymore because it's got a t in front of it. It's not just one constant times e to the 2t plus another constant times an e to the 2t. So I need to show that this satisfies this differential equation. Well, let's do it in general, and then we'll come back. So in general, if I were to solve this homogeneous equation, well, what am I going to get then? I'm going to go back and solve that. That's my, I'm just stealing this from down here, quadratic equation. And if I get two real and the same roots, then, like I got in this situation, then this thing under the square root sign, this b squared minus 4ac, has got to be 0. So I get two eigenvalues, and they're both minus b over 2a. So the only time I'm going to get real and the same eigenvalues is when b squared is equal to minus 4a. And then the solution that I'm proposing here is, I mean, normally we'd do this. Normally we'd take some constant times e to the lambda 1 plus some constant times e to the lambda 2. But now there isn't lambda 1 and lambda 2. There's just one lambda. It's this. So I'm saying throw a t in front. And I need to show you now that this solves this differential, solves the differential equation. That's the auxiliary equation. Let's go get the differential equation. That this solves that differential equation. Well, how do I show you that it solves? I got to sub it into the left-hand side and make sure 0 comes out. So I need the derivatives here. I have y, I need y prime, and I need y prime prime. Now, okay, do I need to show you that this piece solves the differential equation? We already know that it solves the differential equation. I really just need to show you that this piece solves the differential equation. Well, since it's a linear equation, I just need to show you that this piece solves the differential equation. If I can do that, then we already have two solutions, the e to the lambda t, and now this one, when we're done, will be t e to the lambda t, and any linear combination, that's what we're doing here, a constant times e to the lambda t and a constant t e to the lambda t, will also be a solution. We proved that in the last video. So I need to show that this solves this differential equation. So I need its first derivative and its second derivative. So here I got to do product rule. Derivative of the first, leave the second alone, plus the derivative of this, or leave the t alone times the derivative of the second. And now I also need the y prime prime. Now let's collect the pieces together. If I collect the pieces together, there are the pieces that have a t in front of them. So let me just collect those together. So I'm erasing the pieces here that don't have a t, plus the pieces that, so these are the pieces that have a t, and then here are the pieces that don't have a t. That first bracket's going to be equal to, this bracket's equal to 0 because lambda is supposed to be a root of this auxiliary equation. So now it's just a matter of this piece here being equal to 0. But what is lambda? In the case where I get two real and the same eigenvalues, they're both minus b over 2a. So I'll replace this lambda with the minus b over 2a. Now this whole piece here cancels out and gives me 0. So what does this mean? Long story short, this is a solution to this differential equation in the case where we get the real and the same eigenvalues, because both eigenvalues will be minus b over 2a. So then we showed in the last video that any linear combination of two solutions is also a solution. So I can do this, in other words. I can take some constant times the first solution plus some constant times the second solution, and that second solution is t e to the 2t. So this is a solution and it satisfies the differential equation. Alright, now let's bring up the point of linear independence. These two solutions, these two e to the 2t and t e to the 2t, those are two little solutions to the differential equation, but I want them to be linearly independent solutions. So the language of independence and dependence, I think, is lifted out of linear algebra. And if I think of vectors, two vectors are dependent when one is a constant multiple of the other, when they're parallel. So we don't want one solution just to be a linear or to be a constant multiple of the other solution, like we had in the first case we did here. Well, we had identical solutions, e to the 2t and e to the 2t. But if I would have, let's say, doubled one and tried to say, here's one solution, e to the 2t, and here's another solution, like 5 e to the 2t, it wouldn't have worked. They need to be different enough. They need to be independent. How do we test for, in this course, how do we test for linear independence? We use the Wronskian. Now the Wronskian is defined as, I've got it down here again. So the Wronskian is a way to test for linear dependence or independence of two solutions. If the Wronskian is not equal to 0, then the solutions are independent. That's what we want. If the Wronskian is equal to 0, then the solutions are dependent and we can't use them as a linear combination. We don't. Two dependent solutions are, I'm fooling myself thinking that I've got two different solutions. Just like if I had two parallel vectors, I'm really fooling myself thinking I have two different directions. I've got two versions of the same direction. Now I've written, again, there's a lot of linear algebra poking its head up here. Here I've got the Wronskian as the determinant of a matrix. Another way of writing it, if we're not keen on linear algebra, is to just write it as y1, y2 minus, now I'm going to have to put some derivatives, that's y2 prime minus y1 prime y2. So this is a different way of writing a non-matrix way of writing the Wronskian. So if we want to check then that the two solutions that we had, so in our example up here, our two solutions were y1 equal to e to the 2t and y2 equal to t e to the 2t. And if I want to show that these are independent solutions, then I need to build the Wronskian. So I've got y1 and I've got y2. I need y1 prime and y2 prime. So let's differentiate this so we'll have the full pieces I need. So y1 prime, y2 prime, and I'm going to have to do product rule. Derivative of the first, leave the second alone, plus leave the first alone, derivative of the second. So there's my y2 prime. So the Wronskian is going to be equal to y1 times y2 prime minus y2, or let's say minus y1 prime times y2. So I've chosen this way of expressing the Wronskian. When I clean this up, I'm just going to hit simplify. I get equals e to the 4t. More importantly though, not 0, never 0. So yes, these two solutions are independent, and it was okay to do what I did up here with them. And what did I do with them? I used a linear combination of those two independent solutions to solve this second order linear constant coefficient homogeneous differential equation. Now you might say, this Wronskian seems like a bit of overkill here, right? I mean, I just wanted to see if these two solutions were a constant multiple of each other. And when the first time when we did this wrong, I guess, in the first example, when I just used y1 e to the 2t and y2 as e to the 2t, if I would have got the Wronskian for that, it would have gotten to be 0. Yeah, because y1 and y2 are the same, so the Wronskian's obviously 0, but I don't need the Wronskian in that case. I would just look at them and go, oh, the solutions are the same. It's e to the 2t and e to the 2t. They're obviously the same. I don't need the Wronskian. That said, whenever we want to prove that solutions are independent or dependent, the Wronskian's probably the best technique. Let's do an example here where it's not as immediately obvious to us. Here's two solutions. They're 3 cos 2t and sine 2t. Those are both solutions to this linear second order constant coefficient differential equation. And you can verify that on your own. Differentiate both of these two pieces twice, get y1 prime prime, sub it in here, plus 4 times y1, you'll get 0. Do the same thing for y2. They're both solutions. So we know a linear combination of those two solutions is also a solution. But what I want to do is show that these two solutions are independent. That's my question. So I need y1 prime and y2 prime here. If I get the Wronskian of this, I need y1 times y2 prime minus y1 prime times y2. simplify this up. Now this is going to be 6 cos squared 2t plus 6 sine squared 2t. Factor out the 6, sine squared plus cos squared equals 1, and I get 6. Most importantly, I don't get 0. So these two solutions, y1 and y2, are independent. So I can use them, I can use a linear combination of them to solve this differential equation. So let's recap where we are. When we solve a linear second order constant coefficient differential equation, we get our auxiliary equation to get the lambdas. We can either factor or use the quadratic equation. If we get, well, there's 3 cases when I use the quadratic equation or factor. I'm going to get 2 real and different eigenvalues, or 2 real and the same or real identical, so lambda and lambda, or a complex conjugate pair. We know what to do if we get real and different. That was the last video, a linear combination of e to the lambda t's, c1 e to the lambda 1t plus c2 e to lambda 2t. If I get 2 real and identical, now we know what to do. Same idea as with real and different, but we throw a t in front of the second solution. Sometimes people factor out the e to the lambda t, but I don't. But so it'd be c1 e to the lambda t plus c2 t e to the lambda t. Let's do one last example of these real and identical, and then we'll be set. So I need to solve this y prime prime minus 6y prime plus 9 is equal to 0. So we get our auxiliary equation. And I can factor that, and I can see that lambda is equal to 3 and 3. Real and the same, so I'm down with this case here. So our solution's going to be some constant e to the 3t plus some constant t e to the 3t. How do I get the constants? Initial conditions. So the first initial condition is y naught is equal to 0. So when I make t equal to 0, I get out 0. So that tells me that when I make t equal to 0, this piece is equal to 0, e to the 3t is 1. So that means that c1 is equal to 0. The second condition, I need the derivative of this. So I need to differentiate this piece. So that's going to be y prime is equal to, I'm not going to bother writing this down or differentiating it. I already know that that piece is equal to 0. So let's just differentiate this second piece. So derivative of the first, leave the second alone, plus leave the first alone times the derivative of the second. The 3 comes down. When I make t equal to 0 in the derivative, I get 2 out. So 2 is equal to c2. So our solution then, our homogeneous solution is c1 is equal to 0, c2 is equal to 2. This solves this differential equation and goes through the origin with the slope of 2. Alright, I said we were done, but there's one more thing that I want to talk about. I want to talk about the same thing that we ended the last video with. What happens when t goes to infinity? What happens to the homogeneous solution? We already know what happens when we've got a 2 real and different eigenvalues. If they're both negative, the homogeneous solution goes to 0. If both are positive, or if one is positive, then the solution is unbounded or goes to plus or minus infinity. What about in this case with the real and identical? Well, if this eigenvalue is negative, then this piece of the equation goes to 0 as t goes to infinity. That works the same as the time before. But what about here? If lambda is negative, then this t goes to infinity, and e to the minus t goes to 0. So then I'd have infinity times 0. What do I do? Could talk about L'Hopital's rule, or probably the easiest way is the exponential function e to the lambda t is much stronger, goes to 0 much faster than this line goes to infinity. So we can extend our rule. If the eigenvalues, and in that statement I include if they're both the same, are negative, then the homogeneous solution goes to 0. If any of the eigenvalues are positive, then the solution, the homogeneous solution, is unbounded. So that works the same as the last video. So we got one more thing to do. What happens if I get a complex conjugate pair? That's the subject of the next video.